We now have the basic untaxed cash flow model laid out. What we now have to do is consider the discounting. So we're really finished with all the numbers up above. We can put those aside for a moment. I'll take the scale up here a little bit to make it easier to see what we're doing. And now we will simply finish the model. Okay, before we do that, actually one last thing, I'll take that tax rate back down to 0 because we'll be playing with that next week. I don't want to complicate it. We just have to work out the final annual cash flows. This comes in basically 3 parts. We've got the total after tax cash flow. These are future values. Okay, if we look at these, so far we've worked out the cash flow for year 0, which is the purchase event, minus 59,000, so we have a sign on that because these can either be positive or negative. We've got the first year cash flow. We've worked out that equation previously, so we know that's right. So we should be able to fill it across and get all the yellow highlights to run away, and that's all very good. Now we have to discount those future cash flows back to the present, so we'll use the discount factor. Here we've got the equation written in. Let's write that out again, and to do that I'll leave that where it is and I'll just write the first one, which is really interesting, which is the first year one, and that's going to be, now I'll show 3 different ways of doing this. It's 1 over 1 plus I to the n, where I is the discount rate. We're going to eventually be copying that all over the place, so we will make the discount rate absolute, those brackets there, and we will raise that to the year number, in this case 1, so that gives us 0.92, and that's all good. We'll now fill that across. You may want to put some more decimal places in there when you build your own models. I'd recommend don't be excessive there. Maybe 4 significant figures is about as much as is probably warranted. Here we're having 2, and because the model has got protection on this self-correcting one, we can't change that. But when you do your own model, decide for yourself how many significant figures you want to put in. As I say, generally don't put more than 4 because that's getting a little bit silly. We don't have the answers with that level of precision. Okay, we now take the future values and convert them to present values by multiplying by the discount factor. 4,600 multiplied by the discount factor, and that gives us 4,229, and we can fill that across. I mentioned that I would show you 3 different ways of writing this equation, the discount factor equation, which is built from the discount rate. The other 2 is either to leave out the 1 over and to use a negative exponent. That might send you back to your high school maths to remember what negative exponents do, but basically they turn a number into its reciprocal and raise it to the power. So here we're raising it to the power of E12, and we're making a reciprocal, in other words 1 over, by using the minus. That's a little tiny bit tidier, but for people who are a bit rusty with their high school maths, it may not be so apparent. And so you can either use the 1 over form, or you can use the negative exponent, as in what's been done here. Again, the numbers will not change as I send it forward into the future. They're the same. The third way to write this equation is simply to leave out the raising to the power of the number of periods, the year number. It's simply to cause it to escalate from the previous value. So here we have the 1 over form of the equation, here we have it as a negative exponent form, and here what I'm going to do is simply take the previous value, the 0.92, and I'm going to divide that by 1 plus I to the n, so I don't need any exponents. So here we don't have any exponents, which is nice, and that will give us the same number, 0.84. I'll fill that across to illustrate the way that it gives us exactly the same result. I should have 0.77, 0.71, and then 0.65 across here as I fill it across, and you see those numbers have not changed, even though the equation here is quite different. So there's more than one way to skin a cat, and here there's more than one way to write this particular equation. It doesn't matter which one you use, they're all mathematically identical. There may be slight rounding errors at the, 10th decimal place or something because of errors in the way that Excel calculates, but that is not going to bother us at all. Okay. So that means we've got our discount factors worked out, the various ways of putting them together. You can choose which one you want. We've taken the future values multiplied by the discount factors and got our present values. So now we have a row of present values. This means that to work out our NPV, it's going to be a very easy matter because we simply net the present values. Here are the present values, and we simply put them all together, equals sum. We use the built-in function, run across to catch all those. So the NPV in this particular situation is $20,907. So a prudent vendor could put the value up, the price up to $270,000, and a property investor would still be willing to pay, because if they had to pay another $20,000, they'd still have a modest positive NPV of 907, and that's pretty much what we're using this tool to achieve. How much better off am I as a result of buying the investment? There are other ways of calculating this. I'll write one of them over here to illustrate NPV. I can either put in the individual values, or I can put them in as an array. One thing to notice with using the NPV function, the built-in NPV function, when I'm expressing it in these terms, is that the values actually start with year 1, because we're using the net present value of the future cash flow. So here, rather than writing them in individually, I'm going to write them in as an array. That makes it a little bit easier. I will close that. And of course, on top of those future values, I want to net those against the present cash flow, which is minus 59,000. And so that gives us $20,907.28, and you'll notice it gives us exactly the same number as here. Writing the NPV function in this form is a little bit tricky for people that aren't really on top of their game, and the reason is because a lot of people will simply put in this array and they'll put in the whole set of cash flows, including the cost at year 0. But Excel, in its wisdom, only uses this form of the equation in order to work out the discounted components, the ones that are actually happening in the future. And so you have to, if you like, manually add in or subtract the initial cost in this case. A little bit of thought, and maybe going back to your business finance textbook, will sort of explain what's caused Mr. Excel to actually do it in this way. So, which should you use? Well, this form is a little tiny bit cumbersome because we have to put in the discount factors and then work out the the present values, manually and sum them. So it looks a bit cumbersome, but if we use the built-in formula, we have to be on the ball enough to know how to use it. In other words, to separate off the initial cost and then kind of add it in outside the function. So which one looks more complicated to you? Which one do you think is going to cause you more likelihood of error? I'll leave that up to you. There's one other point that I'll make about this, and that is that if you're explaining this thing to a client, laying it out in this way where you have future values, discounting, and then present values makes it considerably easier to explain to a client. And so I tend to prefer this myself, not necessarily because it demonstrates my Excel cleverness, but because it makes it easier when I'm sitting down with somebody across the table and trying to understand why $96,000 is really only worth $62,000 in my model. But a lot of people just don't get that, whereas if you put in this, you can do a better job of explaining it. So in terms of customer relations, I would recommend this approach. Okay, so now we've got the net present value. This next factor, it looks a bit obscure. The annual equivalent net present value. If you go back to your business finance textbooks or other financial management textbooks, annual equivalent NPV will be explained in its purpose. But basically, it's a means of working out how the property is performing on an annual basis. So it's simply dividing the total net present value by the number of years of the project, in this case 5. And so it means that while the project overall is earning you $20,000 above an alternative investment at 9%, that really means there's only about $4,000 being contributed to NPV annually. And that's very useful if you're trying to compare the performance maybe between a 1-year project and a 5-year project or a 10-year project or a 20-year project. The annual equivalent NPV gives you a number that you can compare NPVs across different project lengths. So that's why that is useful. Lastly, we have the IRR. That must be done using a built-in function because it is hideously difficult to work out manually. Maybe in some of the older financial management textbooks you'll find out how to do it. Basically an iterative method, but it's, as I say, a bit tedious, and I don't think in this day and age you would want to do it. You'll either use your financial calculator or Excel or something similar to work out that calculation. There is a trick to working out the internal rate of return for this model, and the trick is that the IRR is based on the future values. And so it's simply, the function is IRR, open brackets, the values running off in the future, close brackets, and there we are. We have 16.72% as the IRR. A very common mistake that students will make is to use the PVs, the present values, rather than the FVs. And as I say, it's a common mistake, but it's one that you don't want to make, obviously. So just remember that. Always use the future values when you're working in the IRR.